Ryoki Professor Fukushima from University of Tsukuba, Japan, and he will talk about annealed random walk conditioned on survival among Bernoulli obstacles. Please.
Okay, thank you very much. Thanks for Yogesh for invitation, and thanks for all the organizers for arranging this online seminar. So this is my second time to give an online seminar talk, so there might be some troubles, but please forgive me about that. And so, for example, even in this first slide, I made a mistake, which is about the date. Date is November 4th, not that. But I hope there is no big mistakes. So I'm going to talk about annealed random walk conditioned on survival among Bernoulli obstacles. And this is based on two joint papers with Jian Ding, Rongfeng, and Changji. So let me start with the setting of the model. The model is very simple. We have only two elements, which are pretty elementary. The first one is a simple random walk on ZD, which I denote by Sn, and probability law is denoted by this bold Px. And in the most of the case, a simple random walk is started from the origin, so we omit this x from the notation, but sometimes it starts from somewhere else. And throughout this talk, I assume that space dimension is bigger than or equal to 2. There is a one-dimensional problem, but it will be quite trivial. I mean, very close to trivial. It's not entirely trivial, but it's much easier than higher dimensional case. So this is our process. And then there is some random obstacles that gives us some random environment, so which is denoted by omega x. And this is just an independent Bernoulli T random variables. P is arbitrary. It's positive and less than 1. And given a realization of this omega, we define a set of obstacles, which is denoted by this script O, as a set of points where omega x takes the value 0. So you can take this omega x as the survival probability, or probability that random walk survives when it hits x. And in this case, it is 0. So it will be immediately killed when it hits this set O. And the hitting time to this set O is denoted by this tau O, which formal definition is given here. And with those ingredients, the question we want to address is the following. How this S, and actually also the obstacles configuration, behaves conditionally on this event, that survival time is bigger than some large n. And more precise formulation is that we are interested in the distribution, joint distribution of S and O under this measure. So we have this product measure, P cross P, with this conditioning, tau O bigger than n. And you see here, we are looking at a product measure at the beginning. So there is, from random walk random environment point of view, we are taking some average over the environment. And in that case, typically this kind of law is called annealed law. And maybe physically, it is more natural to look at the law where obstacles configuration is fixed and only random walk is moving randomly. And that setting is called the quenched law. But in this talk, I will focus only on annealed law. And therefore, this S, random walk, and obstacle set O, both of these moves, we are looking at the joint law. And that will be clear when I show you the first result in this direction. But in any case, the point is that environment is not fixed. Environment is, in a sense, the random walk feels the effect from the environment. But on the other hand, obstacles also feel some effect from the random walk. Anyway, you will see it later. So it's a model of random walk random environment. And let me briefly tell you some other contexts where this kind of problem appears. It's a kind of background. So our killed random walk, if you look at the generator of this killed random walk, then it is at least formally written as a random Schrödinger operator. This 1/2D times Laplacian is just a generator of random walk. And then killing can be described by this potential. It's an infinite potential supported on discrete O. So it's just a formal expression, but you can write the generator in this way. So it's a random Schrödinger operator. For this kind of random Schrödinger operator, there is famous phenomena called Anderson localization, which states that if you look at low energy spectra, then there is a corresponding eigenfunctions in L2, and it's in a sense, they are localized. And actually, the first result for our model is about this probability, just a survival probability. And asymptotics of this survival probability is related to this Anderson localization through something called the Lifshitz tail of the integrated density of states. I will not give you any detail because we are not going to use anything from there. But anyway, there is some relation to Anderson localization. And although this Bernoulli-Anderson model looks most, let's say, at least simple to define, but analytically, this is actually the hardest problem to analyze in the context of Anderson localization. For example, the localization for 2D and 3D Bernoulli-Anderson model has only very recently proved by Ding and Smart. This is 2-dimensional result, and Li and Jian in 3 dimensions. And essentially for IID potentials, these two works are almost the last work in this field. For example, if you replace these Bernoulli potentials by some other potentials, I mean random potentials which have a smooth distribution, then Anderson localization was proved 30, 40 years ago. And it is the singularity of Bernoulli distribution which makes the proof extremely hard. And in the continuum setting, continuous Laplacian plus Bernoulli potential case, even that case has been done only in 2005 by famous work by Bourgand and Koenig. And there is another big step to prove Anderson localization for discrete Laplacian plus Bernoulli potentials, and that is only very recently done.
Ryoki, one question.
Yes.
Can you maybe briefly say what is Anderson localization or localization?
The Anderson localization states the following. So here is a Schrödinger operator, okay? And you look at the spectrum of this operator. And in physics, people are interested in low energy states. You look at low energy, I mean, the spectrum that are close to the infimum of the spectrum. For example, for this operator, this specific operator, spectrum is from, I think, 0 to whole positive line, or maybe 1/2D. But anyway, spectrum bottom is 0. And if you replace this random potential by periodic potential, then all the states are delocalized. There is no eigenfunction in L2. That is classical Bloch-Floquet theory in quantum physics. But if you replace the periodic potential by this random potential, then around the bottom of the spectrum, you see eigenfunctions that are in L2. Actually, not only in L2, but it's decaying exponentially away from some localization center. So there is an eigenfunction, localized eigenfunction, which is caused by randomness of the potential. So that is something called Anderson localization.
Okay, thank you.
So that's the analytical aspect of this problem, but this is not so much related to our result itself. And there is another context, which is a kind of statistical physics context. If you look at our model, this event hitting time is bigger than or equal to n. This is simply equivalent to another condition, which is this one. This S sub 0n is the range of the random walk. So hitting time bigger than n is equivalent to saying that you don't have any obstacles on your range. And if you look at this second formulation, you can integrate out obstacles marginal. What is the probability of this event? This is simply P to the cardinality of the range. So you have this P to the cardinality of the range inside the expectation if you integrate out this obstacles marginal. And then if you look at S marginal, random walk marginal under this measure, then you end up with this expression. It's not so simple to see, but because this P is something between 0 and 1, you can rewrite it in this way. It's just e to the minus nu times cardinality of the range. And in this formulation, this measure can be viewed as a self-attractive polymer model, right? Because here is a cardinality. So if your random walk range has a big cardinality, then it will be penalized. So under this measure, random walk tends to have smaller range than typical behavior. So if you don't like random environment, you can interpret this model as a self-attractive polymer model, which is of its own interest, I believe. So this is the background. And then I start describing our result. So first set result is about the geometry of the range of the random walk under this measure mu. So let me start by reviewing earlier results. So let me recall this mu n is defined as a conditional measure here. And of course, by definition, you can write it as this fraction. And now imagine you have an obstacle which is Bernoulli distributed, and you want to let the random walk survive among obstacles. Now, if the obstacles configuration is typical, then it's like every second step, there is a positive probability that you'll be killed, or random walk will be killed. So it's natural to expect that this probability of tau or bigger than n decays exponentially. Maybe not really exponentially or something like that. So in principle, this fraction is 0 over 0 limit. We want to study 0 over 0 limit. And in that situation, maybe the first natural step to analyze is how fast this denominator going to 0. And that is the first result I want to mention in this talk, which is due to Donsker and Varadhan, more than 40 years ago. So they studied the survival probability, P cross P, tau bigger than n. And they found that this decays not exponentially, but stretched exponentially with exponent d over d plus 2. So it decays like exponential minus constant times n to the d over d plus 2 with a small error. And this constant here, CdV, this you can compute, but it's more informative to look at its variational expression. It has a variational expression which takes this form. So you want to minimize the sum of volume of some set. This is in Euclidean space, continuum Euclidean space. You want to minimize the volume plus the principal eigenvalue, first eigenvalue of minus Laplacian in this set U. I will tell you how this variational problem arises, and also I will tell you why this stretched exponential behavior appears in the next page. But before that, if you look at this variational problem, it contains only volume and the principal eigenvalue of Laplacian. And there is a nice isoparametric inequality, which is called Fabacron isoparametric inequality, which tells us that if you fix a volume of open set U, then it is a ball which minimizes the principal eigenvalue of Laplacian. So I am writing this quite general variational problem, but you can immediately reduce this problem to that for the ball. So it's essentially just one-dimensional variational problem, and you can solve it. So this infimum, okay, this infimum is achieved by a ball with a certain radius, and I will denote that radius by ρ1. Okay. So let me tell you how the proof of this Donsker and Varadhan asymptotics goes, because this is relevant for all the other results. Biggest technicality is hidden, but proof, very roughly, the proof goes as follows. You write this survival probability in this stupid way. You classify everything, you disintegrate everything. So you condition, you look at the event where random walk range has a fixed shape U. And on this event, conditionally on this event, of course, what you want to have is this condition. You don't want to put any obstacle on this set U. And you take this huge sum over U. This is very super exponentially, not super exponentially, it's exponentially large sum. So typically, you don't expect you can read any useful information from this huge sum, but in this situation, you can. Why? Because if you look at this probability, right, this obstacles configuration probability, this you can compute. This is just p to the cardinality of U, as I wrote here. And if you look at the second probability, random walk probability, if U is not too large, then this is almost equivalent to saying that random walk is staying in some region U. Then by Katz's formula, this is the solution to the heat equation. And you're looking at n goes to infinity, long time asymptotics. Then the long time asymptotics of the solution to heat equation is governed by first eigenvalue of the Laplacian because of spectral theorem. Or maybe in this case, it's just the eigenfunction expansion. You expand the solution to the heat equation by using eigenvalues. And if n goes to infinity, there are many exponential terms, but the smallest lambda gives you the slowest decay. So it only matters the first eigenvalue. That's why you get this exponential factor here. So these are two things you have in this sum, essentially. And now if you look at this form, the first factor here, right, this decays very fast. I mean, exponentially if you make U large. If this set U become large, then the first factor decays very, very fast. On the other hand, if you look at this second factor, this goes to 0 exponentially fast in n. But on the other hand, if you make this set U large, then the principal eigenvalue becomes small. Of course, if U is large, then this event is more likely to happen. So this lambda U becomes small if you take U large. But in any case, so this one decays very fast when U is large, and this one decays fast when U is small. So very roughly speaking, we have two exponentially decaying factors, which are decaying, roughly speaking, in opposite directions. And then this is a situation where you can expect to have some sort of Laplace principle. You have a huge sum or huge integration, maybe, where the integrand has exponential decay or some large exponential factor on the top of exponential. And in that case, typically this sum is well approximated by maximal summand. This is what is called Laplace principle. Of course, here it is not trivial at all to establish Laplace principle because we are in the infinite dimensional setting. In the finite dimension, Laplace principle is not so difficult, but here we are working on a huge space, so it's not easy. But this approximation here is what Donsker and Varadhan proved by using the large deviation principle. Large deviation principle is a way to prove Laplace principle in a virtually infinite dimensional space. And if you admit this approximation, you end up with this maximizing problem. And if you put this maximum inside a negative of this exponential, then it becomes infinite. And now in this maximization program, it's obvious that you have to take this set U very large. And the question is how large it should be. if you take diameter of U to be, let's say, R, then this factor becomes exponential to the R to the D. It's just a volume. Radius was R, then it will be R to the D volume. On the other hand, if you look at this factor, if you make U large, radius R ball, then the principal eigenvalue scales like R to the power -2. So in this expression, what you have is R to the D here, and here N divided by R squared. Then it's natural to expect that this maximum is attained by the scale where R to the D is equal to N divided by R squared. And that scale R is given by N to the 1 over D plus 2. This you can compute. Indeed, if you choose R equal to N to the 1 over D plus 2, then volume factor becomes N to the D over D plus 2. And this N times lambda U also becomes N to the D over D plus 2. And taking out that scaling factor, then you end up with this variational expression, which I show you in the previous page. Okay. So, of course, the most difficult part is this approximation, which, as I said, Donsker and Varadhan proved it by large deviation principle. And there is, if we want, there is another proof due to Antar, or I'd say due to Schnittmann, by his method of enlargement of obstacles. So there are two proofs, but neither of them is trivial at all. They are, both of them are quite deep. Okay, but here, what I want to emphasize is not the technical difficulty, but what we can read from this argument. You see, we are looking at this survival probability, and we wrote it as a huge sum. And if you look at this sum, each summand represents certain survival strategy for the random walk, or I would say joint strategy between random walk and obstacles configurations. And what this approximation means is that there is a best survival strategy, and that dominates all the other strategies, actually some of all the other strategies. So this is, I mean, this infimum is achieved by a ball. So the best strategy is to have a ball which is free of obstacles with radius ρ1 times N to the 1 over D plus 2. And the random walk is staying inside that ball all the time. And that's the best strategy. And that best strategy is by far the best strategy, so better than others, so that it dominates all the others. Okay, so from this argument, we read that this survival probability is essentially supported only by best strategy. And then it indicates that if you look at conditional measure, because everything is supported by single best strategy, under the conditional measure, what we see is only this best strategy. All the others have much smaller probability, so we don't see them under the conditional measure. And here is a picture of the best strategy. And this picture is, of course, a little bit misleading, because if you compute the volume of the ball, then it is N to the D over D plus 2. So it is sublinear in N. But on the other hand, of course, the random walk step is size N. So most likely this ball is multiply covered by random walk. And actually not only multiply, most of the point in the ball is visited very many times by the random walk. And the expected number is you have N steps, and there are only N to the D over D plus 2 sites, and therefore typical sites should be visited N to the 2 over D plus 2 times. So it's really many times covered. This picture is completely misleading. So this is a picture we expect from the partition function asymptotics. And some years later, actually relatively long years later, this indicates...
Ryoki, if I may interrupt, sorry.
Yes.
One question is, there is no effect of the percolation phase transition, is it? The appearance of the giant cluster does not change anything in the...
No, not at all. Not at all.
Okay.
Why? Because it is because we are looking at annealed measure.
Okay.
If you look at the quenched measure, it does matter, of course. But here, you see, okay, let me tell you again the best strategy. What is the best strategy? The best, I mean, because we are dealing with this product measure, P tensor P, the best strategy is, in order to make this tau O bigger than n, this is rare event. In order to make this rare event, we decide to pay something to the obstacles configuration and also pay something to the random walk. And what we want to do is to minimize the net amount of our payment. And the best strategy, what was the best strategy? And the best strategy is that we pay so much for the environment probability so that it provides a large obstacles-free ball of radius n to the 1 over d plus 2. And that costs a lot. But once you have this very big obstacles-free ball, then it makes it very easy for the random walk to survive. So it's a balance between obstacles configuration and the random walk probability.
Ryoki, in your picture, you still drew a little few traps inside the ball, but actually that also turns out not to happen, right?
No, that is one thing we want to prove.
Yeah.
It's not clear from this partition function asymptotics.
No, because it's only a density statement. I mean,
Yeah,
you
exactly.
would have very few obstacles, but in fact, there are none. But okay, yeah.
Yeah, that's a difference. Yeah. So it's like a difference between L1 and L infinity. But I want to make sure, Yogesh, are you happy with my answer?
Yes, thanks a lot. It was.
Yeah, always we are looking at a large deviation event. So what happens typically under this obstacles measure doesn't really matter for this annealed model. For quenched model, it does matter. Okay. Now this observation or indication has been made rigorous by Schnittmann in 91 for dimension 2, Borthausen by different methods, slightly different model in dimension 2, and finally by Tobias Pober, who is a student of Schnittmann in general dimension, in the following form, which is actually stronger than what Donsker and Varadhan strategy indicated. So here is a confinement property. This is called confinement. So there is a random center whose location depends on the obstacles configuration, such that for any epsilon, the random walk range is completely contained in this ball of radius rho n. So just as in the previous picture. And this is established. But it took more than 10 years from Donsker and Varadhan. And this is actually much stronger than what the partition function asymptotics indicates. Why? Because you see, if you look at Donsker and Varadhan paper, it is based on large deviation principle. And large deviation principle for what? Large deviation principle for the empirical measure of the random walk. So the best thing you can expect, or whatever you can read from their proof, is that most of the empirical measure is concentrated in the ball, but nothing more, because they are working on the weak topology for probability measures. So in particular, bulk of the mass of local time or occupation time measure, empirical measure, is concentrated in the ball, but that's not enough to exclude the possible excursions. It takes only negligible time, which is going outside this ball. So you can prove that random walk spends almost all the time in the ball, but to prove that there is no excursion at all going outside the ball, it's much harder. And I will tell you a bit more in the next second part of the talk, but there is a nice explanation by Borthausen in his lecture notes in math article, and where he also wrote that it is not clear if one really should believe in this confinement, and had in fact been doubted by experts in the beginning. But this I will try to tell you a bit more in the second part of the talk. Now I'm coming back to Frank's question or comment. So for the same reason, the result doesn't exclude the possibility that there are very few obstacles left inside the ball. But in dimension 2, actually, it was excluded already in the first works. So for example, Schnittmann proves that there is no obstacles left in this slightly smaller ball with high probability. And Bolthausen also proves that the slightly smaller ball here is actually covered by the random walk. So in particular, there shouldn't be any obstacles in this ball, in this smaller ball. So I call this first result as ball clearing and the second result as ball covering. And for Schnittmann, it was kind of small corollary or technical, no, it's a corollary to his analysis, but for Bolthausen, this proposition is actually quite important. Because Bolthausen used this ball covering as a first step for his proof of confinement. So he proves that ball is covered. Then by using that fact, he proves that the random walk doesn't go out. So for him, this proposition is a key step in the proof. And this is the point where his proof doesn't work in higher dimensions. And therefore he conjectured, he left it as a conjecture that this remains true for dimension greater than or equal to 3. Okay, and here is our first main result, which resolves Bolthausen's conjecture. For any d greater than or equal to 2, the random walk range covers this slightly smaller ball with high probability. And of course, this confirms Bolthausen's conjecture in 1994. However, I'm not sure if Elvin will be satisfied with our proof, because our proof relies on the confinement property. Confinement property is proved by another method by Tobias Pobel in general dimensions, and we are using that result. So although we solved his conjecture, but our solution doesn't give him a way to complete his program, so to speak. But it's okay. Recently, Nathanael Verstiki and Rahul Saf announced another proof, completely different technique of proving the ball covering result without assuming the confinement. So this is maybe a better answer to Bolthausen's conjecture. So there are two proofs. But anyway, now we have the confinement property in general dimensions and the ball covering theorem.
Sorry, Ryoki, I'm confused about something. Allow me to interrupt. So the confinement property was proved by Bolthausen also for 3 dimensions, right?
No, Bolthausen didn't prove it because you see here, he needs this ball covering to prove confinement, and he was only able to make it in dimension 2.
Okay.
And the reason is a difference in potential theory. In dimension 2, potential theory is better, and dimension 3 and higher, it doesn't give us good enough control. I will tell you a bit more in the second part of the talk. So his proof works only for dimension 2. So for the proof of confinement property, we have to use a result by Pobel.
Ryoki, one question. Frank answered this question. The center is controlled by the principal eigenvalue. Do you know how close it is to the boundary, or in the middle, or where is it? The xn.
I'm sorry, I don't hear very clearly your question. Xn?
Where is it? Is it close to the boundary, or is it inside the boundary? Frank told me that
xn.
Xn.
Position of xn. Okay, we know the scaling limit of the distribution of xn. It's more likely to be in the center, of course. And its distribution, if you properly scale the space, then its distribution converges to principal eigenfunction of the Laplacian. So it's very nice, curved convex shape and supported in the ball. But it can be close to the boundary.
Okay.
Although the probability is going to 0. Okay, now we have a confinement and ball covering, which means that if you look at the random walk range, its boundary is contained in a rather thin annulus of this form. Range is contained in this ball, and the range contains this ball. So the boundary lies in this thin annulus. So it's a pretty nice, almost complete ball. Then it's natural to study the boundary fluctuation. And unfortunately, boundary fluctuation for this model is extremely hard problem, and we have a rather small step toward understanding surface fluctuation. What we could prove is the following. If you look at the cardinality of the boundary, then it's bounded from above by rho n to the d-1. This is exactly the scale of boundary size of the ball. If it is really a ball, then it's constant times rho n to the d-1. And it is the best upper bound we could prove is log n to alpha. And we have no good control on this alpha. It's very large. It can be very large, but it's polylogarithmic. So it depends a lot on you how to interpret this result. Some people say that, oh, then this boundary should be quite smooth, but I don't quite agree. I don't know. But at least it says that the Hausdorff dimension is not far from d-1. It doesn't deviate from d-1. So in that sense, one might say that it is smooth. So here is this boundary size control. And then I move on to a model with bias. So the model without bias is now quite well understood. And there is another model, a quite interesting model, which is with bias. So our conditional measure is now transformed in this way. So almost everything is the same, but except that we have this exponential factor. H is in RD. And here is this exponential factor, okay? And this exponential factor gives us a stretching force for the random walk, because you see this, if Sn moves in H direction, then this inner product becomes large, so it will get extra reward. But of course, there is this condition, random walk has to avoid obstacles, so there are two effects. And if you introduce this kind of bias, then there is a physics paper by Grasberger and Procaccia in 1982, which predicted that this model undergoes a ballisticity transition with respect to the size of H. And later there are several works, but in particular, Isele and Lang proves that there is a phase transition at the level of partition function or free energy. So at some critical value, the free energy or partition function behaves quite differently. If H is large, then it decays exponentially fast, and otherwise it stays almost the same as Donsker and Varadhan asymptotics. But anyway, I will tell you a bit more in the second part. And the predicted phase transition by Grasberger and Procaccia was made precise by Schnittmann in 1995 in the following sense. So D is greater than or equal to 2, and there exists a compact set K. This measures the size of the bias, such that if bias is in the interior of K, then this Sn is sub-ballistic under this bias measure. And if H is outside K, then it is ballistic. So it's a phase transition. And furthermore, Schnittmann was managed to prove that in the sub-ballistic phase, it is not only sub-ballistic, but displacement is bounded by n to the d over d plus 2. But this is, of course, still a small order, so it doesn't capture right scale for the random walk endpoints. And that will be our third main result. But this small order n to the d over d plus 2 will be important for our analysis. So that's why I'm stating it here. And there is a mysterious compact set K, but this is not that mysterious. We can write it by using something called Lyapunov exponent. So Lyapunov exponent, which we denote by beta x, is defined in this way. So it's a limit of log of P cross P probability that random walk there is something missing, I will tell you. the probability that random walk reach a remote point, nx, before getting killed. You look at this probability, and then this probability decays exponentially fast, because on the way there are many obstacles, and again, every second step there is a positive probability that it will get killed. So it decays exponentially. So I take log, and there is a 1/n missing here in front of log. If you take 1/n times log of this probability, then it converges to some constant beta x. That's just a sub-additive ergodic theorem. And this beta x is something like a time constant for fast passage calculation. But in this model, this beta x measures the costs for random walk to make a long crossing among the obstacles. You have to pay something, but the cost is precisely measured by this beta x. But on the other hand, if the random walk made a long crossing, then under the bias measure, there is this reward, e to the h inner product nx. This is a reward you get. So there is a gain and loss. And therefore, it turns out that if this inner product hx is less than beta x for all x, then it is sub-ballistic, because the gain is smaller than cost. On the other hand, if this inner product hx is bigger than beta x for some x, then random walk gains more than cost if it moves in this direction x. So it becomes ballistic. So this is an explanation of criticality. And I'm sorry, I'm running out of time, but I think I managed to finish my first talk. So recently, there is a very nice work by Fabacron, which pushed forward the understanding of ballistic phase. In particular, they managed to prove that random walk is ballistic even at criticality. Even if h is on the boundary, it is ballistic. And this requires a lot of work. It's quite impressive result. And moreover, in the full ballistic phase, including this boundary case, random walk has an asymptotic speed, so low large number holds. And also they proved that transversal fluctuation converges to a Gaussian law. And their proof relies on some renormalization analysis, which I will not tell you, but it has some similarity to regeneration time techniques for random walking random environment. So if you know a bit about random walking random environment, you can feel something. But it is much harder here because their main focus is on the criticality. And at criticality, the cost is balanced with the gain. So there is no a priori reason to have some effective bias. So you have to create bias, effective bias from nothing. So it's very hard. But they did it. So it's a very impressive result. And in last month, very sad news reached me on October 1st, Dima Ioffe passed away. So I have been working with him for some programs. And of course, for example, this theorem shows that he's a very, very good mathematician. But on the top of that, he's an interesting person. So I miss him a lot. And I just hope his soul stays in peace. But by this result, ballistic phase is fortunately very well understood. And our final result is about sub-ballistic phase. In the sub-ballistic phase, there was a partial result by Schnittmann saying that displacement is small order to n to the d over d plus 2. But if you look at partition function asymptotics, which I will tell you later, it's natural to expect that behavior is almost the same as unbiased case. And this theorem, the last theorem of ours, establishes that. And I think this is not easy to read, so let me replace it by a picture. It looks like this. If it is in a sub-ballistic phase, then with high probability, the random walk is localized in the same ball of the same size, same radius, rho n, as the unbiased case. But the center is, in this case, shifted to the direction of h. And also the endpoint of Sn is shifted to h direction. So this configuration, right, choice of this center and this endpoint is to maximize the gain here. This is the gain you get. So we first proved that it should be confined in the same ball. And among the confinement strategy, this is the best configuration, which maximizes the gain. Okay, so the center in this case is not random anymore, and the endpoint is also not random. But otherwise, the picture is the same as unbiased situation. And in the proof of this precise picture for biased random walk, the geometry of the range result in the first part plays a key role. But in any case, this is the end of my first part. So thank you very much for your attention.
Okay, thank you. So are there any questions?
Yeah, so that's a remarkable result that you say the moment your H is not 0, but it's still in the interior of the set K, then this whole randomness of the center just disappears. It's no longer controlled by the principal eigenvalue, but it's some deterministic point after you scale.
Yeah.
Wow. That's okay, and that will require some serious geometry and serious work to actually make that happen.
Yes, right? Sure. But the real challenge in this theorem is to prove the confinement.
Yeah, yeah.
You see, the Schnittmann's result is n to the d over d plus 2, and our result is n to the 1 over d plus 2.
Yeah,
so
yeah, no, that's much more precise.
But you see, once we could prove confinement, then it's not hard to predict that this is the best strategy. Because as I said in reply to Shiva's question, right, although it was a random center, but the distribution of the center has positive density everywhere.
Yeah.
So it doesn't cost a lot to move this center. But on the other hand, if you look at this gain, right, e to the hsn, if you shift the random center to h direction, you gain a lot. You gain exponential amount.
Yeah, I see. Interesting. Yeah, thank you.
Okay, any other questions?
I mean, again, just the same question I had earlier on this percolation. Sorry, I mean, what happens in the quenched case, just to understand?
Okay, that's the quenched case is very, very different. I can tell you a little bit. Okay, as you see in the annealed case, what random walk and obstacles configurations are doing is the following. You look at product probability space. It's a huge space. And among this huge probability space, two people are jointly looking for best strategy. So in particular, you can explore in the obstacles configuration space. So you try to find the optimal solution in the probability space. Now, if you move to quenched setting, obstacles configuration is given. So you cannot play with obstacles configuration. In particular, you are not allowed to explore in the probability space. Then what you do, you explore a good sort of good obstacles configuration, not in the probability space, but in the physical space. So you look at a huge box. The random walk is given only time n, so you can only explore n by n box, or maybe 2n by 2n box. And inside this huge 2n by 2n box, in this physical space, you try to find a local place, local small region, where obstacles configuration is particularly nice. Nice means it's almost free of obstacles. And then the first question is how large obstacle-free ball? Ball is the best shape, as in the annealed case. So you look for the ball, which is almost free of obstacles. How large ball you can find in n by n box? It's a success consecutive success problem in a coin tossing.
Okay.
So what you can expect is in the volume it should be log n.
Okay.
So in volume, in n by n box, you can find the volume log n ball, which is free of obstacles. And that region is far better than any other places in this physical space. So what happens is that random walk starts at the origin, and around the origin, you don't find anything. The random walk immediately decides to rush to this small region, which is of size log n, but it is free of obstacles. And it rushes to there, and it remains there all the rest of the time. So that is a picture in the quench setting.
Okay, thanks. Very nice.
I have a small question. So there was this thing that you discussed about whether the ball is covered or not, right? I mean, in the d greater than equal to 3. So if we just consider a random walk which is confined to a ball, I mean, we condition that it does not leave the ball of radius sum less than n to the 1 over d, do we know that it will then cover the ball entirely, or is it, what is it, the difficulty, is it about the random walk itself or this obstacle?
No, it's I don't think it's a random walk itself. It's, give me a second. I think, no, it's not a problem random walk. I think in general dimension, if you simply look at the random walk condition to stay in the ball, then I think you can prove that slightly smaller ball is covered by the random walk range. That I think you can find in Schnittmann's book.
Okay. Yeah, no, this is.
But the problem here is that it's not a rigid ball, and also, okay, it depends on the formulation, but in our formulation, there is not only the random walk, but also obstacles.
Okay. Yeah, so that was the question. So yeah.
Yeah, more or less, yes, that's a question.
I see. Okay.
Yeah.
Thanks.
But I think the question is proper in the sense that probably your path in the end looks like a path conditioned on not going out of the ball, and it will cover a slightly smaller ball. I was wondering whether even in the picture that we show now, if you would just say, well, suppose I consider a random walk subject to this drift with this confinement, which sort of is a kind of shadow of what's happening, that you would get the same thing. So of course, in your model, you're clear, your traps are all there, but the moment you've decided that they're outside the ball, is the path then that you get here in this picture simply the path that you would get conditioned on not leaving this ball?
Oh yeah, well,
yeah.
Yes.
Yeah.
I mean,
I
for
so.
unbiased case, it is proved.
Yeah.
In the unbiased case, if you scale the random walk path in a proper way, then it converges to a Brownian motion condition to stay in the ball. Yes.
And that will be the same here with the bias?
With the bias, no, we haven't investigated that.
Okay.
Because, for example, you see, at the beginning, there is certain singularity.
Yeah.
We are starting on the boundary, so it's. If you look at the bulk, I believe that it's simply converges to a Brownian motion condition to stay there, but on the boundary.
Yeah, no, not boundary strictly. Yeah. Okay, thank you.
Okay, so I guess we can take a break now. So it's 11:25 already. Maybe we'll take a 10-minute break and meet at 11:35. Yogesh, is that?
Yeah, I think that's okay.
Okay, shall I start?
Yes, please.
Okay, so welcome back to the second part of my talk. So in this second talk, I explain some proof outlines proofs. And there are 3 contents. At the beginning, I will tell you how the proof of confinement property goes. And this is not our result, but this is to explain a common difficulty in studying this model. And second, I will give a proof for ball covering. And here we use some sort of comparison techniques. So this is a probability model, but in the proof, you will see, I think, more combinatorics than probability. And I hope that makes it more interesting. But in any case, our method is different from many other works in this field. And then after viewing this ball covering proof, I will briefly explain how to prove confinement with bias by using a ball covering type theorem. And in particular, what is missing is the proof outline for the boundary size result. I will not tell you because it requires a bit complicated notation. And there we use quite sophisticated comparison techniques. And my hope is that, okay, anyway, you have to read the paper in order to understand that part. And my hope is that after having this talk, you have a good familiarity with comparison techniques so that you don't have serious difficulties to read our paper if you are interested in. Okay, so these are my contents in this talk. So the first is the proof outline for confinement property. This is Schintman-Pobel and Bolthausen. So the purpose is to explain difficulty. Recall what was the confinement property. Confinement property says that random walk range is contained a ball of radius proportional to n to the 1 over d plus 2. And this probability goes to 1. And according to Bolthausen, it's not clear if one really should believe in this confinement. And I want to tell you why. The general problem in this model is that there are two notions of system size, or there are two separate scales of system size. And the first of them is volume. Let me recall this partition function asymptotics. If you look at this partition function asymptotics, there are this n to the d over d plus 2 appears in the leading order term, and this is in the volume scale, of course. This is just the volume of the optimal ball. And here is an error term, which is just small order to n to the d over d plus 2. But there is another notion of system size. If you are interested in this confinement property, the natural system size is a length scale. And what we want to exclude is the excursion of length n to the 1 over d plus 2. But if you think about it, random walk can make an excursion of this length n to the 1 over d plus 2 with probability approximately like e to the minus n over d plus 2. This is because among obstacles, what you have to do is recall that we are working in the annealed measure. So we can play with obstacles configuration. So if we pay e to the minus n to the 1 over d plus 2 cost, then we can make a cylinder of length n to the 1 over d plus 2, which is free of obstacles. It costs, but you can do it. And then given this corridor, free of obstacles, we can raise a random walk, go inside this corridor and make an excursion and coming back later. It sounds ridiculous, but the point is that we can make it with this probability, e to the minus n to the 1 over d plus 2. And this is much smaller scale than this error term in the Donsker and Varadhan asymptotics. So there is no hope to exclude this kind of event by comparing it to partition function asymptotics, I mean, exact form of the partition function asymptotics. But of course, making corridor and let the random walk go in and back sounds a bit ridiculous. So let me tell you a bit more detail why it's difficult to believe in. If you fix the shape of the excursion, then of course it's very unlikely, or in other words, it's very costly to make this excursion. So it's not difficult to prove that this confinement strategy is better than this strategy. It is almost confined, but make a fixed shape of excursion. This only costs you. So you have an extra cost and therefore it doesn't happen. However, of course, what we want to prove is that there is no excursion. And if you allow one excursion to exist, then of course, there are many other ways to arrange excursions like this. There are many of them. So the first picture here is quite believable, and I think you can even prove it. But it's not clear if one really should believe in the second inequality. There are huge amount of configurations which have an excursion. So there is a, so to speak, in a statistical physics terminology, if you make an excursion, then you lose something in energy. The energy for configuration increase a lot, but on the other hand, you gain a huge entropy. You have a huge possibility to arrange those excursions. And then this second inequality here is not clear at all. And in particular, because this cost of this excursion, each excursion costs only e to the n to the 1 over d plus 2, this error term is far from enough to exclude this kind of excursions. So in summary, whatever you have to prove in order to make confinement is in a much smaller scale than this error term in the Donsker-Varadhan asymptotics. So therefore, we need some new idea for the confinement. It's really not possible to prove this kind of length scale result by using Donsker-Varadhan's result that is in the volume scale. And here is a brief outline of the Schnittmann and Pober's proof, but don't worry, you should be relaxed in this slide because I will not use any elements from this page, just to tell you what kind of techniques exist. So Schnittmann and Pober's proof relies on more kind of analytical aspect of this model. More precisely, they use analytical properties of shredding a semigroup, which is generated by our generator, and strong Markov property at some point. More precisely, the first element, there are three key elements. The first element, I think this is essentially one of the most important elements. It is to find a sharp but non-explicit lower bound for the partition function. So if you look at the partition function asymptotics in explicit form, then you cannot expect much better than Donsker-Varadhan. And also, you see, the first leading order term is in the volume scale and what we want to do in the length scale. So maybe it's not enough to look at the second order in the asymptotic expansion, but we have to look at the higher order expansions, and that looks impossible. And their idea is go to some non-explicit expression. And they were able to find the extremely sharp lower bound for this survival probability in terms of spectrum and some probability. So there is some expectation of the semigroup, which is not explicit, but very sharp. So this is the first step. In a sense, this improves Donsker-Varadhan, but not explicit way. And then for the upper bound, so you have a good lower bound for the denominator. Then now you have to give an upper bound for the numerator. And this part, they use something called method of enlargement of obstacles. This I will not tell you anything. You have to read 300 pages book by Schnittmann to show that one cannot expect more than a single vacant ball of size rho n. What does it mean? From Donsker-Varadhan result, we know that there is an almost vacant ball of size rho n. And in order to create that ball, we have already paid plenty of amount to the obstacles law. We paid some cost. And because it is the optimal shape, there is no point in paying anything extra, roughly speaking. And this is made precise by Schnittmann by using method of enlargement of obstacles in the sense that outside the ball, we cannot expect anything better. So as a consequence, outside of the ball is quite dangerous for the random walk. And this is made precise in a spectral theoretic sense by using his method. But I will not make it precise. In a rough sense, outside is dangerous. And then finally, they use strong Markov property to extract the cost for the first excursion away from the ball. Now, due to the second step, we know that in certain spectral theoretic sense, outside of the ball is dangerous. So if we make an excursion going outside the ball, then you can measure the cost for the excursion. And the most important point of the proof is that this non-explicit lower bound in this first step is designed in such a way that you can compare this lower bound to the upper bound you can gain from this strong Markov bound. And this part I will not tell you, so I don't expect you to understand everything. But the key point is that they get refined lower bound for the partition function, although it is not explicit, and then compare it to the upper bound for the numerator. So in a sense, they still follow usual statistical physics procedure. You study partition function first, and then you can get some information about the Gibbs measure. But anyway, their method is quite analytical, or analytical and probabilistic. And there is another proof due to Bolthausen, which is probabilistic and in some part it's combinatorial. First of all, he obeyed this self-attractive polymer interpretation. He looked at this measure, only random walk marginal, which is expressed in this way. So it's a random walk penalized by the cardinality of the range. And for this model, his argument goes roughly as follows. As I mentioned in the first part of my talk, he first proved that there is a ball covering. The random walk range covers a slightly smaller ball with high probability. And this part actually is done by a little bit of analytical techniques. It's a combination of spectral theory and a little bit of potential theory. The key element is, if you have a completely vacant ball and put a small hole inside, small extra hole inside, then it makes it more difficult for the random walk to survive. And this extra cost is measured by the increase of principal eigenvalue. And it turns out that this increase of the eigenvalue caused by this small hole is measured by the capacity of the hole. Well, in our case, the extra hole is just 1 point. So it depends on the 1 point of capacity of the 1 point built from a large ball. And the behavior of the capacity is very different in 2 dimension and dimension 3 and higher. In 2 dimension, it's logarithmic, and in dimension 3 and higher, it's polynomial. So that's why he was able to prove this ball covering in 2 dimension only. But in any case, suppose you have this ball covering. What he does in the second step, you start with this kind of configuration. You start with configuration of path. You already know that inside of the ball is completely covered, but there might be some excursions. Here are 4 excursions. And then, roughly speaking, he performs a folding operation that maps this configuration of path to another configuration where there is no excursions. For example, you can do it by reflecting all the excursions going outside. Of course, if the excursion is too large, then you have to reflect it many times, but you can do it. And if you do this folding operation, then certainly this reduces the energy or the cardinality of the range. And here we need ball covering property. If ball is not covered by the random walk range, even if you fold outgoing excursions to inside, maybe you don't increase the cardinality if there is something missing in the ball. But here, because we know that inside of the ball is completely filled, if you fold outgoing excursion to inside, then certainly cardinality decreases. And therefore, it reduces the energy. So we gain something in energy, but of course, as I mentioned before, there is an entropy loss problem. If you fold all these excursions, then there is a loss in the entropy. But he managed to prove that gain beats the loss, and this part is extremely hard. He used some refined large deviation estimates for the carefully classified set of excursions and so on, and this part is very difficult. But anyway, he managed to make it. Now, what I want to emphasize about this strategy is that, first of all, it doesn't require fine asymptotics of the partition function. And that is because this argument is, in essence, it is combinatorial. So you start with some unfavorable event where your random walk has some excursions, and you don't compare the probability of this excursion configuration to probability 1, but instead you compare this probability to some other event. Of course, because it is probability, it's smaller than 1, so it's in principle, it's better to compare the probability of this guy to 1, but it turns out that because of this strange operation, it turns out to be better to compare this unfavorable one to favorable one. While the technicality is, of course, quite heavy, but the philosophy is roughly speaking, not use partition functions. Just make a comparison between two events. And you want to prove that some unfavorable events doesn't happen because it has much less probability than some other event. It sounds a bit mysterious, but I will explain. I think I can convince you in the second part of my talk. But anyway, this is difficulty and first case, as far as I know, of the use of combinatorial techniques in this model. And this is due to Bolthausen. Now, I'm going to tell you a rough proof idea for ball covering result. And as I mentioned, our proof heavily relies on comparison arguments. And the real arguments, which I will tell you from the next page, will be quite heavy. So I give you one illustrative example, which is very easy to understand, but I think it's quite illustrative. So here's a lemma, which claims that if one could prove ball clearing, then ball covering almost immediately follows. What I mean by ball clearing means that there is no obstacles in the ball. Here, the first line. Suppose that there is no obstacle in the ball with very high probability. Here is some quantitative control here. So it's not only with high probability, here is some quantitative control, and the law will be clear in a minute. But anyway, if we assume this quantitative version of ball clearing statement, then it almost immediately implies that random walk range should cover this smaller ball with high probability. And this statement, as Manjunath asked, I think there is a way to prove it without using comparison techniques, but I think our proof is much simpler. I mean, we can do it by using potential theoretic, spectral theoretic techniques, but it will be quite not difficult, but it's lengthy. But here's a very simple argument, which I can give you. So suppose that the probability that there is a not non-covered point X in this ball with probability bounded from below. This is what we want to exclude. If we suppose this existence of positive constant C, then here is this existence, but there are at most rho n to the d many points in this ball. So we can put this existence outside the probability in the sense that there is a point such that it is outside the random walk range with probability constant divided by rho n to the minus d. You just take x with the maximum probability, then it's bounded from below by constant times rho n to the minus d. Trivial. And then here is a magic. Well, it's at this stage, it's not the magic. If you look at this probability on the left-hand side, this is bounded from above by another probability, which is this one. So this x in this ball is not covered by the range, and there is an obstacle at x. And here is strange factor 1 over 1 minus p, but I think it's, okay, let me explain in a better way. So here, I think it's good to take p equal to 1/2. Let me take p equal to 1/2. then the obstacles configuration is independent Bernoulli, but in other words, it is uniform. So the obstacles is just uniformly distributed over all the possible configurations. And also random walk path is uniformly distributed over all the possible paths. And now you look at this event. So the probability here is simply proportional to the cardinality of the configurations contained in this event. Now, if you look at this event and compare it to this event, because X is not in the range of the random walk, it really doesn't matter whether there is an obstacle or not, right? So if you look at this event is simply the sum of two configurations where either there is an obstacle at X or there is no obstacle at X. And because they are, it's just a matter of cardinality, those two events has exactly the same cardinality. And therefore, if you look at this event with this new constraint, this set has exactly half of the cardinality compared with that set. Okay? And therefore, if you multiply this probability by 2, if P is 1/2, then this is 2. If you multiply this probability by 2, then you recover this probability. And for general P, I need this strange factor here, but it's okay to take P equal to 1/2. Now, if you understand this argument, now, okay, let's look. This constant times rho n to the minus d is bounded from above by this probability, but this probability is bounded from above by twice of this probability. But what is this probability? This means that there is an obstacle in this smaller ball. And the probability that we have an obstacle in this ball decays faster than rho n to the minus d. So here is a contradiction. What caused the contradiction? It is this assumption which caused the contradiction. So this doesn't happen. And therefore, we conclude that there is a ball covering here. Okay. So I think this is very simple argument, but there are a couple of remarks. We somehow change the point of view. At the beginning, this O, set O, was from IID Bernoulli, but we somehow switched the point of view to the uniform distribution over the configurations. These two are, of course, the same thing, but it's better to change the viewpoint. And also, we are really using that. I mean, in this argument, it is important to follow obstacles formulation. I'm not quite sure how to make this argument in the attractive polymer formulation. We are taking an advantage of working on the product measure space. But anyway, if you follow that, then it's very simple. And this is an illustrative example of our comparison argument. And now, because of this lemma, it's enough to prove ball clearing. It's enough to prove that there is no obstacles in this ball. And this is the aim of the following few slides. So this is to show. And now suppose that there is an obstacle in this smaller ball. Then we make a very simple case distinction. Case 1, we look at slightly smaller ball around X. And case 1, it contains a large density of obstacles. Well, large density is not the proper word. What I assume here is the density of obstacles in this ball is bounded from below by some fixed small constant delta. It has some certain small density, but not too small. And case 2 is just its complement. This small ball contains a small density of obstacles. It's just a case distinction. And then this case 1 is pretty easy to exclude, because you have a big ball And we are looking at a small ball, but still it is of size rho n. So if you have positive density of obstacles in this small ball, whose radius is comparable to rho n, then you lose some volume fraction of the ball because of obstacles. And this means that already in the volume scale, we are away from Donsker-Varadhan optimal strategy. And therefore, if case one happens, then already in the volume scale, it is suboptimal. So this case one can be excluded by simply comparing to Donsker-Varadhan asymptotics. And this is the only place we work with explicit form of the partition function. But this is so easy that we can make it by using that. And now we move on to case two. Case two is of course much more complicated because we assume that there is a small density, but small density does not mean that there is a delta fraction as well, but all the smaller densities are included. So there is no hope to exclude this case by comparing to exact forms of partition function asymptotics. So it's more complicated. And we split this case into two subcases. I will not do it further. So there are only three cases. Case 2.1, there is a small density of obstacles in this local ball here, but random walk comes close to x many times. And case 2.2, it is just a complement. There is a small density of obstacles and random walk comes close to x only a few times. And we will deal with these subcases by using different comparison arguments. So let's start with case 2.1. Just for reminder, case 2.1 is the following. Ball contains a small density of obstacles, but random walk comes close to x many times. And then we are going to do some operation, like Bolthausen did, but it's a bit more complicated because we do it on product space. What we do, we remove all the obstacles in this small ball. Then, of course, we lose some entropy. This operation imposes a cost in the environment probability. We lose some probability in the environment. Or in a more combinatorial way, we throw out certain amount, or actually large amount of configurations, because most of the configuration contains a lot of obstacles here. So this operation imposes a cost in environment probability. But after doing this operation, right, like removing all the obstacles, then we can throw much more random walk passes into our event. Because if there are no obstacles, then it's much easier for the random walk to survive. So we can throw in many passes which are previously prohibited by the existence of obstacles. So in one, this brings a gain in the random walk probability. And technically, this part is quite hard, but it turns out that the gain beats the cost. The gain in the random walk probability turns out to be much larger than the environment probability loss. And in the very, how to say, basic level, this is made possible because we assume that there is only a small density of obstacles, first of all. Because there is a small density, only small density of obstacles, this cost for the environment probability is not too large. But on the other hand, gain in the random walk probability is quite large because I assume that random walk comes close to x many times. So that's a very heuristic explanation why we can make it. But of course, technically, this part is actually the longest part of the paper. And it's not straightforward. I will only briefly explain the reason. The cost for the environment increases linearly in the number of obstacles. If you get rid of k obstacles, then you have to pay p to the k probability to the environment, or maybe 1 minus p to the k. I'm not quite sure. So it's exponential in the number of obstacles in this local ball. But if you look at the gain to the random walk, then it doesn't increase linearly in the number of obstacles, which is sort of obvious because you're looking at a large ball and here's a smaller ball and there are obstacles inside this small ball. But suppose that inside this small ball, the obstacles form a certain blob or cluster, if you want. Then of course, what matters for random walk survivals is the obstacles on the boundary of this cluster. Whatever happens inside the cluster doesn't matter. So what you can expect is, well, at most it is a boundary size. And in fact, if you know a bit about perturbation of Laplacian eigenvalue by perforation, it is actually a capacity of this cluster, not the surface area. Capacity of the cluster that controls the random walk survival probability. And surface area is already sublinear in the cardinality, but capacity grows even slower. So it's even worse. So in that sense, the cost increases linearly, but the gain does not increase linearly. So this poses some difficulty. And technically, it's quite hard, and there is some renormalization techniques we have to use to cope with that. But very roughly speaking, this is covered by this assumption: random walk comes close to x many times. So the gain increases sublinearly in number of obstacles, but we can get some help from random walk. I mean, number of visits of random walk to this ball here. So this is a technically very difficult part. But I will not give you a detail of this technically difficult part because, okay, you can imagine it's technically difficult, but still this operation is in a sense kind of natural. If there are obstacles, then you want to remove it. Then when you remove it, what you can gain is only in the random walk probability. And if there is many visits to this ball, then you can hope that there is a way to make it. So it's a matter of energy. It's not a matter of new idea. But what is more interesting is case 2.2. Here, technically, it's much simpler, but the idea is, I think, new and quite unnatural, which I like a lot. So remember, case 2.2 refers to the case where this ball contains a small density of obstacles and random walk comes close to x only a few times. So this half-sized ball here is this bigger ball in the picture. And in this case, of course, random walk comes close to x only a few times. So you cannot hope to gain a lot in the random walk probability. So we have to do something more, something stranger. And here is our operation, which looks quite mysterious. But you will immediately see that it works. We remove all the obstacles in the annulus here. Then we lose something in the environment probability. And after doing this operation, this annulus is free of obstacles. And then in this annulus, we raise a random walk. Initially, random walk comes inside this ball in this way and going out, but we deform this path in such a way that it avoids this central ball, this gray ball. Now it looks absurd because we already lost something in the environment probability, and now we are losing further in the random walk probability because we are asking something extra to the random walk. So far we only lost something. But after doing first these two operations, then if you look at this central gray ball, it's a paradise. We can do whatever you want. We can do whatever we want. In particular, recall that we started from small density of obstacles. So in particular, the density of obstacles in this gray ball was very small. But after the first two operations, we can recover it to a typical configuration. So for example, if probability P was 1/2, I mean, parameter P was 1/2, we can throw in half of, I mean, we can make the density of obstacles in this inner ball to be almost 1/2. And it is this third operation which gives us a huge gain in the environment probability. The gain in the probability is proportional to exponential to the rho n to the d. And because we assume small density of obstacles, the first operation doesn't impose too much cost. And because random walk comes close to x only few times, the second operation here, deformation of the random walk path, also doesn't cost too much. But in the end, in the third operation, we gain a lot. And therefore, it turns out that gain beats the cost. More precisely, if you look at the probability of this case 2.2, we map any configuration in this event to another configuration, which looks like this. The random walk doesn't hit obstacles, but not only obstacles, but this smaller ball. So this is a stronger condition than survival. And in addition, we have this condition, which is not necessary, but we get it automatically. Now, if you divide both sides by partition function, this becomes a Gibbs measure probability, Gibbs probability of case 2.2. And on the right-hand side, what we get is Gibbs measure. Under the Gibbs measure, which get rid of this hitting time to the obstacles, under the Gibbs measure, the random walk doesn't hit this point, doesn't visit this ball. And the obstacles configuration in this ball is typical. But in any case, it is smaller than 1 because it's probability. And in this way, we conclude that Gibbs probability of this case 2.2 is going to 0. And this operation or this argument for case 2.2 looks extremely wasteful. And actually, I can tell you it is wasteful. Because if you look at the event on the right-hand side, you notice that this event is in the case 1. Because the obstacles configuration in this ball is typical, there is certainly high density of obstacles. So this is in case 1. So what we are doing is very strange. We are comparing this probability of case 2.2 not to the fall probability, but to the probability of case 1, which we have already proved that very, very small. So we are comparing the left-hand side, not to a partition function, but just a tiny fraction of partition function. We know this is the tiny fraction, but somehow it works very well. So the message is that this looks wasteful, but still this is more effective than comparing with the explicit form of the partition function. Okay. So this is the most interesting slide, at least for me. And this shows how the comparison techniques works. There's no partition function appears, but on the other hand, you have to prepare 2 events. I mean, we have to make the right case distinction, and we have to create some target event on the mapping. But it works. So in this way, case 2.1 and case 2.2 are excluded. So in total, we conclude that it's not a good idea to have an obstacle at X. So this finishes a proof of ball covering. Okay. Now, if there is no question, I want to proceed to proof idea for confinement with bias. And here's a reminder of the definition of bias Gibbs measure. Mu h sub n is defined in this way. There is this survival restriction, and on the top of that, we have this exponential factor, bias factor here. Now, let me tell you a little bit about what we can read from earlier works. remember, Schnittmann proved the ballisticity transition, and even more, he proved that under the annealed measure with a subcritical bias, the endpoint of Sn stays within small order n to the d over d plus 2 with high probability. And if you think about it, this morally means that we had this extra exponential gain or exponential weight factor in the Gibbs measure, but under the Gibbs measure, the random walk doesn't move n to the d over d plus 2 to scale. It doesn't move as much as n to the d over d plus 2, which means that when you look at this partition function, this exponential factor doesn't play a big role. If it does, then it should appear under this. It should be observable under this Gibbs measure. So the extra this bias factor is a small order to e to the n to the d over d plus 2. And you can make it precise. And as a result, partition function, if you look at partition function asymptotics, this extra bias term doesn't affect the leading order asymptotics. And therefore, partition function asymptotics up to leading order behaves exactly the same way as the unbiased case. So here we have CdV n to the d over d plus 2, but even this constant dV, Donsker and Varadhan, is the same as unbiased case. So all the effect from the bias is hidden this small order one term. This is already quite impressive. And I think this is one of the motivation for Schnittmann to prove this strange small order type result. And it is quite helpful to us. So what you can read from this leading order asymptotics. As I mentioned earlier, there are two scales, volume and length, and we want to prove something in the length scale. But of course, before do that, you have to prove something in the volume scale. And by looking at this partition function asymptotics, at least in the volume scale, which I call global picture, it should be the same as in the unbiased case in some sense. Or more precisely in the sense that random walks should spend almost all the time in a ball of radius n to the 1 over d plus 2. And I mean, there is a ball which is almost free of obstacles, and random walks spend almost all the time there. This global picture is the same. And everything happens in the smaller scale. So this we can read from this partition function result. And then there is quite a lot of effort to move from volume to length scale, which I'm going to explain. So, okay, I'm sorry, here I'm repeating something what I said. We can read from the partition function asymptotics that there is a vacant ball and random walks spend almost all the time in that ball. But of course, it's not, it doesn't imply that there are no excursions going outside from the ball. And also, in particular, the first piece, 0 to the ball and from ball to the end point should be inside the ball. They are in a much finer scale. And from this global picture, we proceed in essentially 2 steps. First, we are going to prove that random walk from the first visit to the ball to the last visit to the ball. So we are looking at the bulk of the random walk. This should be confined in the ball. So there are 4 excursions starting from the ball and ending in the ball, starting and ending in the ball. These four excursions shouldn't exist. This is the first step. And after doing that, in the second step, we are going to prove that first piece and last piece also must be in the ball. You may wonder why there are 2 steps, why these 2 steps are different. And this I'm going to explain on this page. The reason is very simple. Technically, the excursion starting and ending in the ball is much easier to exclude. Because even if we fold these excursions going away and coming back to the ball, it doesn't affect this exponential factor, e to the hsn. So this folding argument only decreases the energy. Still, we have to control the entropy. But anyway, we don't have to fight with this extra factor. So there is no reason, at least a priori, there is no reason to believe that this bulk confinement is much harder than unbiased confinement.
Ryoki, I have a question, but that's only true when the excursions really recross themselves, right? Because then you say the net result of moving it around is 0, so you can use this mapping that Bolthausen was doing, but that's only when the excursion is a loop, right?
Yes, exactly. Yeah. So that is the definition of the first step.
Okay.
So there are two other excursions or two pieces, which is here, okay, 0 to the ball, and from this y, the last digit to the ball to Sn. These two are different. For these two, we need different technique to exclude. And this, how to exclude this? These two pieces are more difficult because they do contribute to this bias factor, e to the hsn. If we have a long piece from, let's say, y to Sn, then there is a gain. There is a gain of h times Sn minus y, as written here. And we want to exclude this part, this piece, by using subcriticality. Subcriticality means that this gain is smaller than the cost. And the cost is measured by beta of Sn minus y. And because of subcriticality, we know that cost is bigger than gain. But the problem is that this beta, Lyapunov exponent beta, was a crossing cost, but in average sense. So it measures the cost for the random walk to cross in a certain average environment. And because we are working under different Gibbs measure here, so we cannot simply apply this average crossing cost immediately to this piece. In particular, if there are many excursions, I mean this loop excursions, going outside this ball, then if you have some strange environment, let's say around y, then it might help to have these excursions. It might help these excursions. So under the Gibbs measure, there is no a priori reason to believe that outside the ball is an average environment. So that is a difficulty. We want to use subcriticality, but we have to prove that there is, I mean, what we have to prove is that we can discuss the bulk of the random walk, which I mean, I want to prove that it's confined, and the first and last piece is separately. And we want to prove that they depend on the disjoint part of the environment. And actually that is the role of step 1. If we manage to prove this step 1, right, random walk is confined in the ball from first digit to last digit, then in this bulk, it doesn't go outside. So the bulk of the random walk doesn't interact with first piece here and the last piece here. So these three pieces depends on the independent environments or disjoint environments. So that's the role of this first step. So after making this first step, we can treat these three pieces depending on independent environments. So we can apply Annealed Lyapunov exponent results for first piece and the last piece. And by using subcriticality, we can prove that it's better not to have pieces going outside. So here we don't use any folding argument. It's not a folding, but just a subcriticality, which excludes these two pieces. So here is a bit schematic picture. So the overall argument goes as follows. Here, we start with this environment, sorry, this configuration. And we first prove that it's better to fold these loop excursions, according to Frank, to inside. We should fold these excursions to inside, and we end up with this picture. But if you look at this picture, as I said, these three pieces of random walk depends on the disjoint part of the environment. So we can apply Lyapunov exponent, I mean control on the crossing cost by Lyapunov exponent to this first piece and the last piece. And then by subcriticality, we conclude that these two first and last pieces shouldn't exist because it's, the gain beats, sorry, the cost beats the gain. So if you believe this schematic picture, I'm hiding a lot of technicalities behind, but if you believe this two steps picture, the most important part is to prove the first step. So the confinement of the bulk of random walk. And here I roughly follow Bolthausen's proof of the confinement property. Because there is a bias, so the partition function is not as nice as Schnittmann's work. Oh, I'm sorry, I think I'm running out of time, but I'm finishing in a minute. So let's recall Bolthausen's strategy. We prove the ball covering first, then do some folding argument. So what? So we have to prove ball covering under the bias measure. So here's the lemma. This is a key lemma. We have to prove ball covering under the bias measure. And this tau b is the hitting time to the ball, and this tau inverse b is the last visit to the ball, which is the same as a first hitting to the b of a reversed random walk. So this is what we have to prove. And after having this ball covering, we can follow Bolthausen's strategy, roughly speaking. Now here is the final remark, how to prove ball covering. The proof of this ball covering, previous lemma, is fortunately exactly the same as unbiased case. Why? Because our proof for unbiased case was essentially combinatorial. In particular, we didn't use any partition function asymptotics or spectral theory, which becomes quite nasty if you add a drift to the operator. We don't use that. We are using combinatorial techniques. So the proof is almost exactly the same. So there is no extra effort to prove this ball covering, and then we are done. And this is really a good part of this combinatorial proof. It doesn't force us to work with non-symmetric operators and so on. So in that sense, I don't know if the large deviation argument, which Bolthausen and Beresicki have used, works for this bias measure or not. Okay, I'm sorry for overtime, but thank you very much for your attention.
Okay, so maybe we can take a quick question, if any.
Yeah, I was wondering, Ryoki, does this fine surgery that you have now done, does that actually allow you to say what the next order term in your partition function would be? Or are you saying, no, we have just been sort of excluding strategies and we're not getting enough information to do that?
Yes and no. For bias case, my answer is no. My strategy of surgery here is really in order to avoid partition function.
Yeah.
So even though we get quite fine result under the Gibbs measure here, it doesn't say much about the asymptotics of the partition function. And one of the reasons is, of course, this, what we are dealing with is this gain here, e to the HSN gain. But you see, what we have proved is that this gain part is e to the n to the 1 over d plus 2 length scale. And this already shows that this effect is hidden in a very, very higher order term in the partition functions. And there are many other, surface order term and maybe capacity order terms and so on, which should be identified before. So in that sense, this result itself doesn't say anything about the partition function.
Right.
Another result of ours, this one, boundary size result, this has some implication to the partition function asymptotics.
Right.
And this I didn't tell you because it's not trivial, but still it's very suboptimal.
Yeah.
So okay, we wrote this in, we wrote that implication in our paper, which appeared in PTRF. But okay, yes, from this boundary size result, we can reach something. But
Okay,
from,
but you say it's suboptimal because of this extra logarithm that you don't control. Very
yes, partly yes.
well.
But there is, okay, I can tell you. So if you look at this Donsker Varadhan, what is expected is the following. There is a physicist paper which says that, okay, leading order term is n to the d over d plus 2. And the second order term, by some field theoretic non-rigorous argument, someone derived that second order term should be, first of all, it should be negative, okay, minus some constant, times n to the d minus 1 divided by d plus 2. So it's a surface order.
Yeah.
And what we can prove by using our boundary cardinality result is the following. Okay, there is a known result. The lower bound of that form, I mean negative and surface order, lower bound is known. It's not difficult to prove. But upper bound in the same scale is missing. And what we can prove by our boundary result is that we can get an upper bound, which looks like this reading order term n to the d over d plus 2, and second order term, we don't know it is positive or negative, but okay, for the upper bound, it should be positive. It is bounded from, partition function is bounded from above by here plus constant times n to the d minus 1 divided by d plus 2 times log n to some power. This is what we can prove by using boundary result. And previously, what was known is that second order term is n to the d minus kappa divided by d plus 2. Kappa is between 0 and 1. So it's a slight improvement.
Okay, thank you.
But it's not great.